Okay, hello. My name is Ahmed. I'm from Triple E, and I'm going to talk briefly about gallium nitride-based laser diodes. It's a quick review about these devices. I will go quickly during my content. I will have a brief introduction about the topic. After that, I will talk about basic geometries for laser diodes, properties and issues for gallium nitride-based materials required for deposition and fabrication of laser diodes. And at the end, I will introduce a short case study about indium gallium nitride based laser on silicon substrates. So the idea behind this review is to make successful integration of gallium nitride based laser diodes into the mature silicon technology, silicon photonics. Of course, silicon technology is mature and well established, and there exists huge industry investment in this field. This is because of the smart properties of silicon materials, such as hardness, thermal, electrical properties, and mechanical properties. This image here shows an example of silicon photonics, which includes a single substrate, includes filters, laser devices, modulators, CMOS or transistor circuitry, and photodetectors all in one device. It's a large volume or large scale which requires special treatment and special fabrication procedures. So that the larger scale photonic devices require manufacturing of high quality laser diodes to be fully integrated within these photonic devices, and such applications require as telecommunication, sensing, space applications require implementation of high power laser diodes on these silicon chips. So these require materials that are robust, have radiation, thermal stability, and chemical stability, and all these properties are acquired inside gallium nitride based materials. These materials are expensive. Yes, of course they are expensive, but they have superior properties. These superior properties, as we will see later, make them a very good candidates for deposition of silicon of laser diodes on silicon substrates, and also these properties make some issues during fabrication of the device, as we will see later. So it's a demand for gallium on silicon technology is rapidly increasing, as you can see in this chart, which shows global gallium nitride on silicon technology market uh, classified by regions: North America, Europe, Asia Pacific, Middle East, and South America. As you can see, from 2018 until 2026, the demand for gallium on silicon technology is increasing, and the investments are a lot. So this is very appropriate to know that there exist two basic geometries or structures for laser diodes, for the conventional on-chip laser diode structures. They are named edge-emitting lasers and surface-emitting lasers. This is with respect to the chip alignment. The first type is the edge-emitting lasers. From its name, it's edge-emitting, so light output is emitted from the edge. As shown here in this figure, we could see that the output beam propagates parallel to the chip surface and is emitted from the device edge. The active region here is a multiple quantum well from material, quantum well material, and a barrier material for confinement of light, for confinement of stimulated emission stimulated emitted photons, and the optical cavity is created by two coated facets. This facet and the other one here, they are coated, cleaved and coated, high quality coating, in order to acquire the optical cavity, which is a Fabry-Perot cavity. The laser output is elliptical. As we could see, this elliptical output because of the width and height aspect ratio is very large. For example, we could see height width to height ratio could be 80 to 1, which is very large. So this output is elliptical, and this laser type provide a high gain and high power laser. Type is the surface emitting laser devices, laser diodes. And in this type, The active region also is a multiple quantum well, but the optical cavity is different from the edge-emitting laser. The optical cavity here is and confinement of light is two distributed Bragg reflectors. This is the top distributed Bragg reflectors, DBR, and this is the bottom DBR. They have high reflectivity and allow light to bounce back and forth between them, and then the output laser emitted from the surface, and this is called surface emitting because output laser or light propagates perpendicular to the surface of the chip. This is silicon substrate, so light is propagating perpendicular to the surface and output from the top surface of the device. One problem for this device is that it provides low gain because the light confinement is in very narrow region, which is active region. It's very narrow, so it provides a challenge for achieving the threshold, which requires good control to reach this threshold. And on the other hand, for the beneficiation of this type over the edge emitting laser, it provides better device stability and lower cost. So the one of the best materials to fabricate laser diodes on silicon chips is gallium nitride materials, which gallium nitride materials are made by gallium nitride and its ternary alloys such as aluminum gallium nitride or indium gallium nitride, or even quaternary alloys such as aluminum indium gallium nitride. The properties for these materials are common. For example, as we see here in this figure, these materials can structural properties or structural arrangement can come in three different arrangements: the hexagonal vorticite, the zinc blende, and the rocket salt. And the most stable among all these in room temperature and pressure and ambient pressure is the hexagonal vorticite, where we could see that each gallium atom is surrounded tetrahedrally by 4 nitrogen atoms, and the same for nitrogen. Each nitrogen atom surrounded by 4 gallium atoms. And for the layered structure of gallium nitride materials, we could see that they arrange in the AB configuration along this 0001 direction, as we see here in this figure, where AB is gallium nitride, then on top the top layer will be another gallium nitride, AABB gallium nitride, then gallium nitride, then gallium nitride, and so on. This is the layer structure in this direction. So these materials exist in the hexagonal vorticite structure, which is the most stable crystallographic structure for these materials. Optically, these materials have wide and direct band gap of 3.39 electron volts, which is wide in the UV region, and this band gap actually could be tuned by changing the metal concentration in the alloy. Before we go through this, we could see from this figure that this is the calculated band gap structure, band structure for gallium nitride. We see that the valence band maximum and the conduction band minimum are on top of each other in the K vector, so that this is a direct band gap material. We mean that, for example, if we take aluminum gallium nitride as example, and X is the metal concentration or aluminum concentration in the material, if we change X, consequently gallium will change. So aluminum will change and gallium will change. So we could say that aluminum gallium nitride, a ternary alloy, is between gallium nitride band gap and aluminum nitride band gap. So if the concentration of aluminum is 1, so we are talking about in aluminum nitride, and if concentration of aluminum is 0, we are about gallium nitride. So we can tune the band gap of aluminum gallium nitride from 3.4 electron volts for gallium nitride into 6.11 electron volts for aluminum nitride. As we could see here, we can tune whatever energy band gap we need. And hence, or consequently, from this, coefficient and refractive index can also be tuned by changing the band gap, because there's a direct dependence between these. So we could see, as we could see from these figures, that the refractive index could change with changing aluminum concentration, and also it's changing with changing photon energy which represents the band gap, and also the absorption coefficient increases. Here it's very sharp in the UV region, and you could see that it's tuned to the lower UV wavelengths with changing the band gap of the material. So these properties, as I said in the beginning, are superior for optical applications such as laser devices, but also they are considered some issues during the integration with silicon photonic devices, especially with silicon, because there is a lattice mismatch and thermal mismatch for gallium nitride with silicon. There is high resistivity of the p-doped materials and also optical losses in the p-doped layer. Quickly, the high p-doped material resistivity is due to the low concentration and low mobility of holes inside these materials, and these materials are lossy because of the high coefficient of absorption coefficient of these materials, which by time affects the light extraction efficiency and hence the quantum efficiency or quantum yield of the device. But the most important one we need to focus on in this mismatch and thermal mismatch of the device. As we could see here, the lattice mismatch is 17%, which affects the cluster quality and morphology. Actually, when depositing gallium nitride over silicon substrate without careful control of the deposition process, we could have low crystal quality and poor morphology. And thermal expansion coefficient mismatch is 54%, which is very large. This allows the increase of trading dislocation density, which is not desired at all for such light emitting device, and also it allows the formation of crack network. So both these lattice mismatch and thermal mismatch can cause bowing and cracking in the substrate, especially for large scale substrates. Imagine an 8-inch silicon substrate, and we are depositing gallium nitride and any gallium nitride material on top of it. We could see that this high lattice mismatch and high thermal expansion coefficient mismatch can cause cracking and bowing for such 8-inch substrate. So some solutions for deposition, not all solutions, and not all of these what I'm going to say are efficient, but there are some solutions is are to make use of a nucleation or buffer layer, which is the most common one is aluminum nitride on top of the silicon substrate. This aluminum nitride can block the interdiffusion of gallium inside silicon and silicon inside gallium, which is not acceptable, as this interdiffusion allows for the creation of leakage current, which is not wanted at all for device operation. So aluminum nitride buffer layer can help reduce crack network and help reduce the stress in the layers. Also, good and careful control of metal concentration internally alloys, such as aluminum gallium nitride, as we said, can be used so that we can compensate the tensile strain that is created in gallium nitride layer after deposition by a compressive strain which is induced in the layer and then reduce the bowing probability. Also, we can use silicon 111 orientation instead of silicon, for example, silicon 100 or silicon 001, because silicon 111 has a 6-fold symmetry and gallium nitride itself has 6-fold symmetry. So this allows for deposition of very or highly stable hexagonal vorticized structure, which we need for our devices. So, as a case study, I said I'm going to say a case study at the end. As a case study, Yisan and his group in 2016 have successfully fabricated an edge-emitting indium gallium nitride-based laser diode on silicon substrate, which is very suitable for silicon photonic integration as it can operate under continuous wave current injection at room temperature. The device fabrication and the epitaxial structure was grown by metal organic chemical vapor deposition technique on silicon 111 substrate, so that this, as we said, can produce better vorticized structure. This MOCVD deposition started by aluminum nitride buffer layer, so he can now stop interdiffusion of gallium inside silicon, and then step graded to aluminum gallium nitride layers. These are what, as you could see in this figure, silicon substrate on top of it aluminum nitride, and followed by aluminum gallium nitride step graded layers, and then thick gallium nitride waveguide and gallium nitride doped silicon cladding, and the active region with a multiple quantum well, as we could see, we will see, and then the top cladding and the contact layer. The thick aluminum nitride buffer layer was 280 nanometers, and the step graded aluminum gallium nitride layers are with aluminum concentration of 0.35 and 0.17, so that threading dislocation density is reduced. So I could repeat, the reason for using such step graded aluminum gallium nitride layer is to stop or reduce at least the dislocation density in the structure. As we know that the threading dislocation is a dangerous thing in the light emitting device, as these threading dislocations act as non-radiative centers, and this can sometimes quench the light extraction efficiency and even any light emission. The active region, as I said, is a multiple quantum well of indium gallium nitride with concentrations x equals 0.1 for the quantum well layer and x equals 0.02 for the barrier layer in the multiple quantum well. And a thick gallium nitride and aluminum gallium nitride doped with silicon are used as waveguide and cladding for better optical confinement of the device. After that, they have done dry etching, photolithography, and thermal evaporation in order to be able to deposit the SiO2 isolation layer. This is the SiO2 isolation layer for this device. They actually fabricate different devices beside each other, so they need isolation for each single device from the other. So they deposit SiO2, and then the thermal evaporation is used to deposit the metal electrodes for electrical injection. The optical cavity is created by cleaving the facets. This image shows how the facet cleaving, as we see here, smooth and cleaved and coated face. As you see, the color difference between this top cross-sectional part, and this is the facet, the cleaved facet. Facets are cleaved, and then high reflectivity coating is done for the front and back facets, and they got reflectivities of 70% for the front facet and 95% reflectivity for the back side facet. Okay, this device structure allowed for reducing the threading dislocation. This was the main problem they discussed in their work. They included in their work to decrease threading dislocation density in the fabricated device. As you could see here, this is threading. The image is the electroluminescence image shows the threading dislocation density distributed on a single part, 1 micrometer part of the device of the surface. Threading dislocations are low. This image shows that threading dislocations are considered low. And as I said, this threading dislocation, if exists in the material, they act as non-radiative recombination centers and can quench the internal quantum efficiency of the device, and also can reduce the injection efficiency. Another thing for the device characterization, in this part they have made a simulation for the electric field distribution in the device and which layer of the device have the highest electric field distribution, and they found that most of the electric field is confined near the active region. This is simulation data, and as we could see, this is the electric field, and it's confined in the This is the cladding, and this is the active region limits, and the electric field is confined in this region. Electroluminescent measurement is done for device fabrication in order to see whether the device is lasing or not. And the spectrum is shown in this figure. It's seen that they have injected current starting from 50 milliamperes until 160 milliamperes. It's seen that the electroluminescent spectra by increasing injection current, the emitted spectrum intensity developed and increased, and also there is also a shift here by increasing the current injection. The wavelengths, the emitted or the peak wavelengths shift towards lower wavelengths, but the shift is very low. And also the full width at half maximum of the emitted peak intensity gets narrower. They have seen that for the light current voltage measurements, they see that this is a pulsed current injection, and this is a continuous current injection. The continuous current injection shows a well-defined stimulated emission kink, and this observation with a full width at half maximum decrease with increasing current injection means that the device is lasing or in the lasing operation. And also they have characterized the light voltage curve in order to see how the device degrades. They found that for the continuous wave injection operating device, the degradation occurs faster than the pulsed operation mode, especially for higher injection regions. And they have deemed this to the heat increase to the as injection increases, the localized heat in the device increases, and this allows for the regeneration of some threading dislocations, and this causes some injected electrons to recombine before reaching the active region, and also this allows impurities to diffuse. The increased temperature allows impurities to move to, if they are, for example, if some impurities are localized in their space, when we increase the pressure we give them energy and they can move, but in this time they move or diffuse in the active region and reduce the device quantum efficiency, which is not desired. So this requires another study for enhancing device degradation and increasing lifetime. So as a conclusion, we could say that gallium nitride materials are desired for on-chip laser diodes for silicon photonic integration, but this requires good control for the device fabrication, device design, material content, and also heat treatment in order to annihilate or at least reduce as much as possible the threading dislocation density in the device, and hence increase the quantum efficiency and light extraction efficiency and quantum efficiency of the device. Studies showed that the use of silicon 111 substrate and aluminum nitride buffer layer are good solutions for better device structure and performance, and also further improvements are required for the active medium or to enhance the active medium region in order to enhance the device lifetime and limit the degradation of the device. Thank you.